So continuing on with our lecture, we are talking about soil structure. And when we talk about soil structure, we've already kind of been mentioning it so far, but really it comes down to pore space. And the idea of making sure that we have plenty of space for macropores, which are big pore spaces, and then micropores as well are little pore spaces. Macropores, for the most part, are all about holding air and transporting water, whereas the micropores are really bigger on water retention. But the way that it really just works is that air is going to occupy any pore space that water isn't. And so when you have a really wet soil, the macropores are filled with water, and you don't have a lot of air. But if you have a dry soil, you got a lot of air and not a whole lot of water. For trees, it's best to have a balance of both. So for trees, you'd want this well-structured soil here. We got our nice soil aggregates. We've got space for these large pores where we got lots of water in there, but we also got some room to have air in there as well. And we got our air and our water and our nutrients stored in the micropores and the macropores. If we have poorly structured soil, water's going to pull up at the surface and maybe even create surface runoff. It's not going to be able to leach and get things down to the other layers below, and everything's just going to move very slowly, whereas water has good mobility through this well-structured soil. Just taking another look at it here on the left, good structure. Water moves through soil with good structure, nice and easily. Here's a look at a soil aggregate and kind of the idea. So sand, some silt, some clay particles all mixed together, and then you've got the space in between, the pore space for the water and for the air. So on the left, unstable aggregates lead to reduced infiltration, not that easy to get through, whereas here you see that nice soil look to it. It's got kind of that granular look to it, or maybe more of a little blocky sort of texture, where it's good texture. The soils are aggregated, which means we're going to have pore space and plenty of places for the water and air to move through. Big concern with soil structure is surface compaction. So surface compaction happens when the aggregates are destroyed and the fine soil particles end up creating like crust. The example they give is shingles on a roof. But the big thing for this is you get inhibited water filtration, and you get compacted soils. So with compacted soils, roots aren't able to stretch out as much. They're restricted. You get reduced water infiltration, mobility, and availability. All those things are reduced with compaction. You get limit the movement of oxygen and carbon dioxide in the root zone, which is extremely important in terms of the air movement throughout the soil. And then your macropores that also get used up by the larger organisms or by organic matter, things like that. That pore space, that aeration capacity is reduced. So in looking at these soils here, let's think about the most to least compactable soil. So 1, 2, 3, 4, 5. So pause real quick and see what you get. All right, let's check our answers. Here's our combination here: 1, 2, 5, 4, 3 for most to least compactable soil. So number 1 here, 100% clay, is always going to be our most compactable soil because of that high surface area. Also, you're going to end up with a high bulk density because it's a clay soil. Number 2, you got 75% clay and 25% sand. Sandy soils usually aren't subject to compaction, but this is a mostly clay soil. Our next soil over here, 50% clay. So that's our next highest amount of clay. And then our 25% clay and our 0% clay. Basically, the more clay you have, the more likely you are to end up with compaction. because of that high surface area and that platy structure of the clay. One too far. There we go. Back to it. All right. Soil pH. Soil pH is the single most important chemical property of the soil. The things we've been talking about up to now have been the physical properties of the soil, but chemical properties of the soil. Soil pH is the most important chemical property. It affects chemical, physical, and biological properties of the soil. pH will affect which species grow and which organisms are present within the soil. Soil pH will determine your nutrient availability. And if you're just unaware of what pH is, so it's a measure of the acidity or alkalinity of the soil. So we talk about soils being either acidic or basic or alkaline. Alkaline's another way to say that. And so it's a scale that ranges from 0 to 14. 7, which is what water is neutral, so it's neither acidic nor basic or alkaline. And anything less than 7 is going to be acidic, going from very acidic down by 0 to slightly acidic around 6, 6.5. And anything above 7 is going to be alkaline or basic. So each essential element is available for uptake within a relatively narrow pH range. So it's going to be something like, this one's available from 3 to 5.5 in pH, or this one's available from 6 to 8.5, something like that. At certain pH levels, essential elements form chemical compounds that are insoluble in water, and thus they become unavailable for the plants to take up through the roots. And that's important because that's how the plants get their minerals, is they get them through the soil, through the roots, because the roots can take up minerals that are, it's basically the minerals are in solution in the water, and then the roots can take up the water. But those minerals are only available at certain pH levels. So for example, in highly acidic soils, so something with a pH of 5.5 or below, phosphorus may be deficient, while other elements may even become toxic, like manganese and copper. So what are we talking about? It's this idea right here. So if we look at some of our essential elements, our essential minerals and nutrients that we need to see in our soil, we've got nitrogen, phosphorus, potassium, calcium and magnesium, sulfur, boron, copper and zinc, molybdenum, iron and manganese, and aluminum over here on the left. And so if you look here, you can see, well, we're pretty good at 6.5 to 7. If we're 6.5 to 7, we're solid. Even with 6, we got some light brown here. And actually, we can really go up to like 8. We're all good. But anything outside of that, we start becoming nitrogen deficient on the acidic side and molybdenum deficient, and anything above 8 really suffering in terms of copper and zinc, and then iron and manganese. And aluminum is only available to things that are really acidic. So it's interesting that that's just the way soil's going to work. Phosphorus got to be needed in a really basic soil. And so it's just kind of interesting the way it works. So when a soil is acidic, minerals such as iron and manganese dissolve in soil water in small quantities. These minerals help plants grow. However, when the soil becomes too acidic, these minerals become so abundant that they can harm or even kill the plant. And so it's just kind of like everything else. Everything within limits. A little bit of something is good. A lot of something is usually bad. And so overall, what are we talking about with trees then? Trees usually grow in slightly acidic soils, and the best soil for tree growth would probably be something with a pH around 6 to 6.5, which you can see right here is pretty good for almost all of these except for aluminum. So just to give you an idea of what soils look like throughout the U.S., the North American average is about a 6.4. So for North American soils overall, it's a slightly acidic soil. You can see in California here, our soils are actually more towards the basic side, where you know, you're probably somewhere around a, give or take a 7.2, something like that on average. And you can see there in the southeast, very, very acidic soils down in the southeastern U.S., much different from what we're seeing. California, much different from what you'd see in Texas too, which is more like a 7.5 on average. And then of course, these states over here, well, why don't they show up? They're white, and they're missing stuff, and that's because you got really mountainous soils, or you got desert, so it doesn't really jive with the what they're trying to show here. So while a soil pH around 6.5 is often considered ideal for plants, many trees can grow well at soil pHs above 7, although like we said, 6 to 6.5 is ideal. As pH levels increase above 7.5, most trees will experience some sort of nutrient deficiency, often iron and manganese, which become lacking once it gets that high. These elements are available in high amounts and very easily available when it's slightly acidic. But when it gets that alkaline, they're not available anymore. Elevated soil pH may result in chronic long-term issues like chlorosis, low vigor, poor growth, stem dieback. We'll start seeing some of those problems, and it might be that all you need to do is fix the pH, and hopefully that's an easy fix with some sort of soil amendment. And amending the soil, sulfur can lower pH, lime can raise it. That's kind of just a basic thing. Sulfur will lower your pH, and lime will raise it. That's not the solution for everything, but it's a good generality. There we go. So plant growth and nutrients. Soil is going to provide plants with the physical support of plants. The idea that the roots are going to dig into the soil, and that's going to help anchor in the plant. It's going to provide water and air to the plant, and it's also going to apply or supply essential elements to the plant. So what essential elements? So it's going to supply the macronutrients, nitrogen being the most important and the most abundant one that the soil is going to provide the plant with. But then your other macronutrients are phosphorus, potassium, calcium, magnesium, and sulfur. Some people look at calcium, magnesium, sulfur as secondary nutrients, and it's really just NPK, nitrogen, phosphorus, and potassium as your macronutrients. If you look at any bag of fertilizer, it's some sort of mixture of NPK, nitrogen, phosphorus, and potassium, because more than likely, if you can keep those macronutrients in good amounts, then you'll be off and running. You also have micronutrients that are good to keep an eye on: boron, copper, and iron, chloride, manganese, molybdenum, and zinc. And interestingly enough, these are the 16 essential nutrients for maximum plant growth. And because we eat a lot of plants, and a lot of people these days have your plant-based diets and all of that, that these macronutrients are also, macro and micronutrients are also the nutrients that are important to us as well in terms of how we function as human beings. Cation exchange capacity. Really important in kind of going back, and we talked about the idea of clay, and clay having a high surface area, and clay also being the idea that when clay gets wet, it gets sticky. All those ideas kind of play into this idea of cation exchange capacity. So you have minerals that are required for tree growth, those essential elements that we just covered. They dissolve in water, or they're in solution. That's what solution means, is that you have something that dissolves in water. And so because they're in the water, in solution, they're available for absorption by the tree roots. So you got charged particles called ions, and you got negatively charged ions called anions. The positively charged ions are called cations. And so it's important to understand that that clays are usually negatively charged colloids. Colloids just being that they are a group of something within something else, but it's a group of something microscopic for the simplest kind of version of what a colloid is. But it's negatively charged, and then cations are positively charged. And so the cation exchange capacity is a measure of the soil's attraction, retention, and exchange of these positively charged cations, because you've got the clay in the soil being negatively charged, and you've got these positively charged cations, so they will attract each other, and then that's how the soil is able to do this exchange with the roots of the tree, and with the being able to exchange the mineral elements within the soil. And what's important about cation exchange capacity is it's a gauge of our soil fertility, so how healthy, how vigorous our soil is. So you can see I just like this diagram. I think it's kind of fun, the idea of the essential elements just being the letters, and the tree roots trying to get into the soil and get after all of them. We've got our essential macronutrients right there, the N's. You also got your K's and your P's and all your other stuff that the soil would be interested in. So kind of still sticking with the idea of cation exchange capacity. So you got your cations, these positively charged ions out here. You got your negatively charged soil particle, or your colloid. And so what you got is, because these are negatively charged, the positive charged ones get pulled right in, and because clays have that high surface area, there's lots of room to do these chemical reactions. Organic matter also, it's organic matter and the clay particles that carry a negative charge. So both organic matter and clay are extremely important in this idea of cation exchange. Fine textured soils that contain a relatively high proportion of clay and or organic matter will tend to be more fertile than coarse textured soils, or soils that are very sandy, because they've got this high surface area. So they're going to just be more fertile because they've got more of this negative charge that's readily able to accept these positively charged cations. So sand particles conversely have little electrical charge. Sandy soils tend to have a lower cation exchange capacity for this reason. And a lot of that with the sand particles is due to leaching, and leaching just being washing through the soil. The idea that things will kind of move through the soil quickly, and so because that happens, sand does not do cation exchange capacity well, because it doesn't have this high surface area. It doesn't hold things well. It doesn't have these negatively charged particles ready to accept all these positive cations. Another thing that's important to look at is the idea of soil salinity. So how much salt do we have in the soil? It's a measure of the soil salinity is a measure of the quantity of mineral ions dissolved in the soil solution. Soil solution just being water. Mineral ions in the soil are essential to plants, but excess quantities can be harmful, which we talked about earlier with pH. And so salinity, we're really measuring that idea. Do we have the right amount, or do we have excessive amounts? Certain types of soil have a tendency to accumulate soil salts to excessive amounts. There's the idea of salinity. And we don't want to accumulate salts to an excessive amount, because that can basically just poison our soils. So the recommended treatment for this sort of thing is to leach them through the soil solution with a low salinity water, or you basically just flush the excess salts through the system and kind of spread them out enough, or spread them deep enough that they work their way through the soil and kind of spread out, or work their way all the way out of the soil. In terms of biological properties, lots of things going on in terms of soil biological properties. Soil is an ecosystem, and it contains billions of organisms. The majority of the organisms being directly or indirectly beneficial. Like I said before, it's a very symbiotic ecosystem where everything kind of has a hand in helping everybody else out. So that's why it's the majority are directly or indirectly beneficial, not some are good and some are bad. The majority of things within the soil are beneficial to the soil. When we say organisms or we say microbes, what are we talking about? Talking about insects, mites, millipedes, earthworms, fungi, bacteria. They all inhabit the soil and litter layer. They all increase aeration, and they accelerate the decay process, which is all part of the carbon cycle, which is good because they get that organic matter degraded. They turn things like leaves and twigs and scat and all of that stuff, they turn it into humus, and then it becomes part of that surface litter layer, and then that eventually becomes part of our topsoil as well. You also have nematodes, microscopic roundworms. Those sorts of things can parasitize tree roots and sometimes transmit disease. So like we said, the majority are beneficial. Some things in the soil aren't as beneficial. But then again, that's some nematodes. Other nematodes, however, will feed on pathogenic and disease-causing organisms and are beneficial to the tree because they go and find things that are doing bad stuff to the tree and they actually eat them. Bacteria and fungi. It's important that we mention both of those because if it's grassland dominated, it's mostly bacteria. If it's forest dominated, it's mostly fungi growing beneath the soil. But both of these are important. They're an essential part of the balance of life in the soil, helping to decompose the organic matter and aid in the nutrient uptake. Fungi, especially with the idea of mycorrhizae with the tree roots in a symbiotic relationship. The mycorrhizae is the symbiotic relationship between the fungi and the roots, where it almost is, the fungi acts like an extension of the roots. And basically what the roots offer the fungi is protection and sugars from the photosynthetic process. And then the fungi acts like an extension of the roots, grabbing up more water and more essential elements for the tree. So nice, good relationship there. And just a quick little soil food web, right? So here's our decomposition happening. We get some leaf litter dropping. That's going to become the top part of our surface litter layer, eventually using some of these organisms and microbes to decompose that stuff and make it into humus, and then eventually it becomes part of the topsoil. And then we also have all this other stuff happening where we got this eats that, this eats that, this eats that, eventually this eats that, and then this bits and pieces of these things die and also become organic matter, or this thing poops stuff out. Actually, all of these things poop, and all of that stuff all becomes organic matter, and it's all part of the soil food web. And it all leads to that idea of how important organic matter is and the carbon cycle within soil. So the rhizosphere. Oh, my fault. The rhizosphere, just some of the good things and the bad. So some of the good things that you get with your rhizomes, sometimes they can cause plant diseases. Sometimes you get even opportunistic human pathogens, things that can really screw things up for us. But good things, you get activation of defense, you get plant growth promotion, efficient nutrient uptake, abiotic stress tolerance, disease resistance. You get these through plant beneficial microbes. You get biotic interactions and plant diversity. but you can have some problems. You can get plant parasitic microbes, and you can get those human pathogens we talked about. And you also have all sorts of other things that we can do above the surface that will also affect that. But in terms of the rhizomes and what they do, in terms of the roots and how they're working, there is a good, bad, and ugly of it, but it's much more good than bad, and then definitely the ugly when you see the size of this circle. Much more good, a little bit of bad, or a bit of bad, and just a tiny bit of ugly. So we talked about mycorrhizae before, but mycorrhizae literally translates to fungus roots. They're specialized root structures. It's really just a symbiotic relationship of fungi and the plant roots. It's created when a mycorrhizal fungi infect the roots of a suitable host plant. Most plants have associated mycorrhizae, specifically, like we said, in forested soils. You can expect this mycorrhizal relationship, or any kind of woody plant. You can expect the mycorrhizal relationship. In grass, you expect more of a bacterial relationship. Mycorrhizae fungi live in a symbiotic relationship with the roots. The fungi and the roots both benefit from the relationship. The roots, we talked about this before, the roots provide a place for the fungi to live, and they provide its sugar through the idea of photosynthesis from the tree, and the fungi increase the capacity of the roots to absorb water and essential elements, especially the element phosphorus. They're really helpful in finding phosphorus and gathering up phosphorus for the plant. Just another look at the idea of nutrient cycling, which ties into the soil food web. So we get water and air penetrating the soil. We also get dead plant and animal matter hitting that surface litter layer, then becoming humus, and then eventually becoming topsoil. We get plant growth. We get the rocks breaking down and building more soil. We get decomposers, all those microorganisms that we talked about in the soil breaking down organic matter so that it becomes essential nutrients again, and then we got minerals and other nutrients that are released into the soil or released into the plant, helping the plant grow. And that's how we kind of we cycle through nutrients within the soil. Humus, you've heard me talk about it. Here's a picture of it, because you look at it and you go, well, yeah, it looks like there's like a couple pieces of twigs and some other stuff in there, but then there's some stuff in there where it's like, I'm not quite sure what that used to be. And that's what's happening. It's not quite surface litter, and it's not quite topsoil yet. It's that in-between stage. So we just call it humus, or the definition of humus being partially degraded organic material. But why do we like humus? Why do we think organic matter is important in the soil? And it's important because organic matter can absorb more water per unit than clay. It's got a really high capacity to absorb water, and it's really important. That's also why when we're planting trees and we're using something like mulch, why do we mulch around a tree? And it's because it can hold more nutrients, and it has high water absorbing capacity, and it reduces soil temperature. It's all those sorts of great things that mulch provides. And humus does the same thing. It doesn't have that plasticity or stickiness that clay does, and eventually it will just degrade to carbon dioxide and water if it's aerated and if it's got the presence of oxygen. So this will continue to degrade into topsoil and essential elements if nothing goes wrong, as long as there's that presence of oxygen. In terms of urban soils specifically, as opposed to the soils in forested areas, urban areas may be altered in such a way to become unfavorable for tree growth and development. Things to remember: urban soils usually lack an organic layer because you might not get that growth at top. It might just be you're just getting a little bit of a leaf drop and that sort of a thing, or maybe not even if you got heavy conifer trees, or you have heavy landscaping going on where they're clearing off all the debris that falls down. You also are going to probably deal with issues of compaction or crusting or shrink swell, or maybe even some hard pan sort of things, elevated pH, altered drainage for sure, root issues, disrupted soil profiles, chemical contamination, subsurface barriers, due to things like building foundations, road, underground utilities, pipe systems, those sorts of things, and all those sorts of things that come with development or urban development that you don't quite see just out in the forest. So here's kind of a good example, right? It's hard to have an organic layer when it looks like this. Now it's not, you can still get water in here, you can still get air in here, so your soils, and they're using this metal grate, which will hopefully keep down on compaction of the soils, but you are lacking that organic layer. So it just kind of depends on what exactly you're looking at in terms of your urban soils. But turf, bare ground, and or pavement may replace that organic layer, because you can see we're also then surrounded by pavement here, which then could create some issues in terms of your roots spreading out and your fine roots, your fine absorbing roots, and how far they have to go. Paving may impair aeration and water filtration. Organic matter reduction decreases the biological activity and hampers soil structure development, interrupts nutrient cycling, and can affect your soil pH. And then urban soils may also lack the microorganisms, and may even lack mycorrhizae, because it just might not be enough of it available to make it to make that symbiotic relationship happen. Compaction is definitely a huge issue in urban soils. How do you get compaction? You get it through foot traffic or vehicle traffic or construction activities or poor management practices, or you can also get it with areas that just aren't managed well, like you get an area that floods all the time, and then people you get flooding all the time, and then foot traffic, so you get this combination of the soil getting just messed up and pounded together. Why is compaction problematic? Compaction breaks up those soil aggregates, so instead of having, here's our piece of soil and a piece of soil and a piece of soil, and we've got a macro pore and tiny micro pores, everything just gets kind of pushed into one big thing. And if compaction gets bad enough, especially like here in the Central Valley, it ends up just becoming one big piece of soil, and that's how you get a hard pan layer or a traffic pan if it's due to like vehicle or foot traffic. And then you get that increased bulk density, limited gas exchange, limited aeration capacity, because you don't have good macro pores anymore. And then you also get reduced water infiltration and water mobility and permeability into the soil. Your compaction of soils is a leading cause of tree decline in urban areas. So you really have to, if your trees are having problems, there's all sorts of things to check in terms of the soil to see if that is the cause. And lack of water, lack of air is going to be probably right up there for a lot of the issues that you see. And compaction problems are definitely best managed by not getting the soil compacted in the first place. It's hard to fix once it's happened. It's kind of a thing you're going to just have to adjust to more than you're just going to fix it. I talked about this idea before, but the macropores being the large pore spaces between soil aggregates that allow water, air, and root growth. And if you see right here on the right, so you got surface rooting trees growing in these compacted soils. And so you want these soils, you want your roots to be able to spread out and grow and find space. And you can see like everything is really shoved together here. And it's not, when you look at the soil here, we want to see like big want to see aggregates. We want to see pieces of soil, whether they look like columns, or whether they look like plates, or whether they look like like cookie crumbs, or whatever it is, granular, spherical, anything. If you look here, this is much more of a kind of a massive look, where it's just kind of pushed together, sort of a thing. It doesn't have like a good structure to it. And when you don't have a good structure, you're not going to have a high aeration capacity. And aeration capacity is just going to be how much large pore space or how much macro pore space do you have. And so you're not going to have good aeration capacity if you don't have good soil structure. Soil improvement. So how do you actually improve some soils? Poor drainage is going to be a common problem in urban soils. Your options to correct poor drainage are going to depend on the nature of the drainage problem and whether the goal is to correct the problems prior to planting around established trees. Basically, you'd like to fix problems before the trees go in there. If the trees are already in there, and now you've got poor drainage problems, now you can make your fixes, but they're going to be more expensive, and they may involve a lot more work than if you could do it beforehand. In many cases, your poor drainage is going to be caused by the subsurface soil compaction during construction. In the absence of established trees, pipes, or other underground utilities, tillage with a rototiller, subsoiler, or disc harrow can improve these conditions, because you're basically going to open up pore space and try and basically try and get the soil to clod up, which is you're kind of making artificial soil aggregates, and then in doing so, that will open up the pore space again. In small areas such as landscape islands, a backhoe or an auger may be used to dig, lift, and replace the soil, and just kind of move the soil around and give the soil another chance to get water and air in there and aggregate up to really try and open up that macro pore space and that aeration capacity to really allow the soil to drain well. Amending soil or making soil improvements using organic matter provides multiple benefits, such as improved water infiltration, water holding capacity, aeration, and enhanced cation exchange capacity. And so one of the good ways to do that is just by using the compost. Incorporating organic matter is relatively inexpensive and pretty easy to do. We see people kind of doing it all the time. The organic matter is incorporated in the soil at a rate of about 15 to 20% or less by volume. Often incorporation is quite shallow around trees, but deeper is better if practical. So we were talking about mulching before, and you want to kind of pile your mulch up. You don't want to just spread out a nice thin layer. You want like a good pile of mulch around your tree. The effects can be long-term, but are not usually permanent. And if you're using organic matter, what's nice is it will decompose. The soil will shrink some, but you put it in there, and it eventually just adds to the soil, which is nice. Mulching the surface with an organic mulch, like we were just talking about, many beneficial effects. Can reduce surface compaction and crusting, improves water infiltration, reduces soil erosion, decreases weed competition, and then the temperature fluctuation. So soil temperature, you don't really see the effect of the daily fluctuations. Daily fluctuations meaning like it's cold in the morning, then it heats up in the afternoon, and then it becomes cold again at night. Really, if you have a good layer of mulch, it's just going to be kind of one temperature throughout the day. It's not going to have a fluctuation, or at least it's not going to have a big fluctuation. It'll maybe just change by a few degrees as opposed to like 10 or 15 degrees. Over time, your soil structure is going to be improved, and mulching may decrease soil surface pH on excessively alkaline soils as well. So if you have a really, really basic, really, really alkaline soil, you want to get it to be a little more acidic, adding in this organic matter mulch is going to help decrease your pH. Another issue that's often discussed is the idea of soil modifications. Unfortunately, little long-term data is available to guide recommendations, and it gets to be really site-specific in terms of the duration and what you're going to get in terms of your soil amendments. And so your modifications can be considered long-lasting. Sometimes they're going to work really well, sometimes they won't. It's kind of hit and miss because soils are so different and they're so site-specific sometimes. It's just, you got to kind of try some things and really figure it out. You got to come up with what are your good management practices and what's best for the soils that you have. You really just kind of have to come up with cost benefit. What's going to benefit, what's going to cost, and just make sure that your benefits always outweigh your costs. And that's what I got for you. It's a lot. But soil is extremely important. It's extremely important for urban forestry. It's extremely important for forestry. It's extremely important just for overall ecology and understanding of natural resources and the environment.